Okay, let's continue. So I want to do an example. So here's an example. Let's take A to be 1, 5, 6, 2, and let's have U be 6, negative 5, and V is going to be 3, negative 2. Okay, so I want to know if U and V eigenvectors of A. Okay? Okay, in other words, does A just scale these vectors, or does it rotate them too? If it just scales, then they're eigenvectors. So let's check. So here's the solution. Just compute A of U. Okay, so this is going to be 1, 5, 6, 2 times 6, negative 5. What do you get? So you have to do the row column rule, right? So what you get is, check your answer, negative 24 and 20. Okay, so make sure that you're able to compute that. Okay, so negative 24 and 20, you can factor out negative 4 from that. Okay, that's the common factor that these guys have, and what you have left with is 6 and negative 5. Okay. 6 negative 5 is exactly U, so this is negative 4 times U. Right? So you can see that this multiplication doesn't rotate my vector at all. It just scales it by negative 4. Okay, so from this equation, A times U equals negative 4 times U. I get that, yes, it is an eigenvector, right? So U, so this equation is the definition of an eigenvector, right? So U is an eigenvector with eigenvalue negative 4. Okay, so negative 4 is like my lambda in this case. Okay. Okay, let's do the next one. What is A times V? Okay, so you just write it down. Okay, what do you get? Okay, again, do the row column rule. What you get is negative 9 and 11. Okay. Now compare this with your original V. So you can see that this is not a scalar multiple of this. Right? There's no way to get from 3 to negative 9 and also get from 2 to 11 with the same scalar. Right? So this is not equal to lambda times V. Okay? So if A times V is not equal to lambda times V, okay, remember this is the definition of an eigenvector. Right, so V is not an eigenvector. Okay? All right, let's continue this example. Okay, so another example, I'm going to use the same matrix, okay? So I'm going to take the 1, 5, 6, 2 matrix, okay? And what I want to do is I want to show that lambda equals 7 is an eigenvalue. Okay. And I want to find the corresponding eigenvector. Okay. So here's how to do this. Okay, and the way that I'm going to do this is the way that you're going to do any of these problems where you want to show that a given number is an eigenvector. So here's how it goes. You want to solve a times some x is equal to lambda times that x. Right? In this case, I'm given lambda is 7, right? But let me just leave it as lambda for now. Okay, I want to solve this for x. Right, so I'm given lambda. Okay, in this particular problem, lambda is 7. Okay, so here's how to do it. And it's a little bit tricky. The trick is that x is the same thing as the identity matrix times x. Let me write that down. This is equal to the identity matrix times x. And the reason for this is that the identity matrix doesn't change x. So x is equal to the identity matrix times x. Okay, now what I can do is I can move everything over to the left side. So I subtract this from both sides. What do I get? I get a times x minus lambda times the identity matrix times x equals the 0 vector. Okay, now I'm going to factor out x. So I have a minus lambda times the identity matrix times x equals 0. Okay, look at this. On the left side is a matrix. I have a matrix, it's kind of a weird matrix, but it's a matrix, times x equals 0. And we've had a lot of practice over the course solving equations of a matrix times a vector equals 0. Right? So this is the equation I'm trying to solve, okay? Okay. So think of solving, think a times x equals 0. Right? This is the homogeneous equation. This is the type of equation we've been practicing a lot. So just replacing your a by this funky matrix, we can solve this problem. So let's write it down in this case. So a is 1, 5, 6, 2. Lambda is 7. And the identity matrix, the 2 by 2 identity matrix, is 1, 0, 0, 1. Right? So a minus lambda times the identity is just this matrix, 1, 5, 6, 2 minus 7 times 1, 0, 0, 1. Right? Which is, so let's simplify this a little bit, 1, 5, 6, 2 minus Okay, multiplying a scalar by a matrix, you multiply every entry. So this is 7, 0, 0, 7. Okay, so matrix subtraction, I just subtract all the entries. So what do I get? I get 1 minus 7, so I get negative 6, 6, and then 5, and looks like negative 5, right? Alright, so if I'm going to solve this equation, this is the equation that I need to solve, right? Okay, that equation is just negative 6, 6, 5, negative 5 times x equals 0. Right, so these two equations are the same. I just had to simplify this funky matrix, right? Okay, now I know how to solve this equation. So this is an augmented matrix. Negative 6, 6, 5, negative 5, 0, 0. And then I would do some row operations to that. Okay. So if you do those row operations, you get this. 1, negative 1, 0, 0. Okay. So now you want to find the solution to this. Right, so you write down, what were you trying to find? You're trying to find x. X is my eigenvector, right? So what's the general solution to this? Well, as you can see, this is a pivot, and x2 is going to be my free variable, right? So the first equation I would write like this. x1 is equal to x2, so just solving this equation for x1, and then x2 is free. So x is equal to x1, x2. Okay, so I'm going to write everything in terms of my free variable. So I'm going to be, this says that I can replace x1 by x2. So this is x2, x2, and then I'll factor out x2. x2 times 1, 1. Okay. So this vector, okay, this is my eigenvector. Okay. So let's check that this is my eigenvector. Okay? So let's check. So what did I say? I said, so I'm going to check my answer. So remember my A was 1, 5, 6, 2. And lambda was 7. And I just computed that the eigenvector was 1, 1. Okay? So we're going to check that that worked, right? So if this really worked, then when I multiply A times V, I should get 7 times V, right? Alright, let's check it. So let's multiply 1, 5, 6, 2 times V. Okay, what is that? So if you do the row column rule, what do you get? got it? 7, 7, right? You pull out your 7, you get 7 times 1, 1, which is, sure enough, 7 times v, right? So it worked. Okay? So v is my eigenvector. Okay, so even more, I showed, so if you remember the last page, my solution set to ax is equal to 7x was any scalar multiple of 1, 1, right? So 1, 1 works, but any scalar multiple does too, right? So this, any scalar multiple of this vector, is a line. Okay? So 1, 1 points in this direction, and then any scalar multiple of it will form this line. Right? So in other words, this is the span of this one vector. Okay? And this is a subspace. Okay, it's a subspace because it goes through the origin, and it satisfies the other definitions of a subspace, so you can take two vectors in this line and add them together, you get a vector in the line, right? So this subspace is called, this is called the eigenspace. So there's a lot of eigens in this section. Okay? So let me formally define the eigenspace. Okay? So here's your definition. So I'm going to take an eigenvalue of A, just like in the last example, my eigenvalue was 7. Okay. Okay, so I'm defining this. Okay, the eigenspace of this eigenvector is, well, how did we do it in this case? In the last example, what I computed was I solved the equation A minus lambda times the identity equals 0, right? If you remember that, I had this matrix times x equaling 0. So that is nothing other than the null space of this matrix. Okay? So if you forgot the definition of null space, this just means all x such that this matrix minus lambda times the identity times x equals 0. Okay? So in this case, I got, in the last example, I got all scalar multiples of this vector. So this eigenspace of 7 is a line, and it's spanned by the vector 1, 1.